Hello, this is the graph analysis and vocabulary video, part 2. So for part 2, we are starting on example 4, as example 3 should have been completed in class. So for example 4, this is a good example of a non-calculator question where we're talking about max and mins. So we have been given a graph. Now I'm not sure if you can tell, but this right here says f prime of x. So that's the graph that we have. And again, it says it down here at the bottom, graph of f prime. Now for me, I see that and I acknowledge it, but what I like to do is write that this is the derivative. So whatever I need to know, I'm going to use the graph of the derivative to find the information out. And again, this is the graph of the derivative, not the function. So we're in an interval from 0 to 10, which means we probably need to check out some endpoints. We have a semicircle of radius 2, that's fabulous. A line segment mean at the point 4, 0, and the right endpoint is at 10, 2, so we know exactly where that is. So for part A, for what value of x between 0 and 10 does f have a local minimum? So first thing I need to start out with is, well, where are my critical points? So I'm going to look at the graph of my derivative. My critical points, critical numbers, are where the derivative is equal to 0. And again, I have the graph of the derivative. So where the derivative equals 0 would be at this point right here, my derivative is 0. And this other blue point right here, my derivative is 0. So my critical numbers are at x is 0, and we have another one at x is equal to 1, 2, 3, 4. 4. So at this point, we need to determine whether we have a local minimum or a local maximum at each of these values. So let's look at what happens to my derivative. And I'm going to kind of use a sign chart to talk about what happens. And I'm just going to put it next to my graph right now. So I know what happens with my f prime, which is going to tell me what happens with my f. And the critical points I have are at 0 and 4. So after x is 0, which would be the red portion of the graph, what's going on? Well, my derivative is below the x-axis, which means my derivative is negative. So my derivative is negative between 0 and 4. However, after x is 4, my derivative is above the x-axis, which means my derivative is positive. So after x is 4, my derivative is positive. So let's talk about what that means for my function. My function between 0 and 4 is decreasing. And then after 4, because my derivative is positive, my function is increasing, which means we have a local minimum at x is equal to 4. So I need to justify that, and we may never justify our answer with just a sign chart. Never just a sign chart. Okay. Which means I need to use some words. So let's use our words to explain what we just did. So we have that f has a local minimum. So first we need to answer the question, does it have a local minimum? Yes, f has a local min at x is equal to 4 because the derivative changes from negative to positive at x is 4, which means now I need to talk about what that means about the function, which means f changes from decreasing to increasing, making the a local min at x is 4. And if you need time to write that down, go ahead and pause your video now. So for part B, For what value of x, between 0 and 10 again, does f have an absolute maximum? So now we need to figure out, well, okay, where's my absolute maximum? Well, I know it's not a 4 because that was a local minimum. So I need to be looking at my endpoints. So let's look back at the graph. And again, this is my derivative. I'm going to erase what I have. And I want to find the maximum. And looking at my sign chart over here, I know that I am decreasing from 0 to 4. So I probably need to look at 0 as a possible max. But then again, after 4, the function's increasing, so here is a possible max. So what I actually need to do is I need to figure out how much the function decreases after 0 and how much the function increases from 4 to 10. So let's look at our graph. In our graph, if I wanted to know how much the function increases from 0 to 4, I would need to calculate the area that is below the x-axis. So let's go ahead and calculate that area. That area, I'm going to kind of look at my graph and look down. My radius is 2, I believe, and I have half of a circle. So f decreases from x equals 0 to x equals 4. The area under the curve, which is 1/2 times pi times the radius squared. So my function is going to decrease by 2 pi. Okay, so that means at x equals 0, the function is 2 pi higher than the function is at 4. So let's figure out what happens after x is 4. So looking back at my graph, I should be able to identify the shape that's created after 4, and this shape is a triangle. They gave me some points, so the segment I just drew in should have a height of 2, and then the length of the base should be 6. So I should be able to find the area of that triangle. So I know that after x equals 4, the function increases by 1/2 6 times 2 until it gets to x is 10. So at x is 10, it's increased by, looks like 6 units. So f increases from x is 4 to x equal 10 by that area, which is 1/2 base times height, which is 6. So the question is, basically what we have going on, just as a quick sketch, this doesn't mean anything. I don't know where anything is, so it's really the the x-axis isn't relevant. So if I start up here, then if I go down here at x is 4, the distance that I have traveled must be 2 pi. So this has to be 2 pi higher than wherever the function is at x is 4. But after x is 4, the function is going to increase until x is 10, and this is going to increase by 6. So the question is, where's the absolute maximum? Which is higher, 2 pi or 6? So the absolute maximum is at x is 0, because it's 2 pi higher than the min, whereas at x is 10, that's 6 units higher than at x is 4. So the absolute maximum is at x equal 0, because f decreases more between x equals 0 and x equals 4 than f increases between x is 4 and x is 10. Now, again, if you need time to write that down, pause the video here. I'm going to move on to example 5. So for example 5, we are calculator active. So if you do not have a calculator, pause the video, go grab a calculator so that you can work this out. It will be helpful if you use your calculator to do this as opposed to just watching me. So in this one, we're starting with a rate. We have a rate. So if you think about it, our rate isn't the amount of water that we have. The rate is in gallons per hour. So our time interval is from 0 to 3. We have the equation for the rate, and we have the rate that the water flows out is given by S. We know that our tank initially has 10 gallons. So when is the rate at which the water flows into the tank the greatest? Okay, so that's going to be, and again, I need to kind of pay attention. The rate at which the water flows in. Well, the water flowing in is also a rate, so I definitely want the derivative of R, and I want to set it equal to 0. Okay, so it's the rate of the water flow, and that's going to be the derivative of R set equal to 0 to find when we have a critical number for a possible max or min. So the first thing is I need to find the derivative of R. So R prime is going to be a product rule. So why don't you right now go ahead and do the derivative of R, please. And the derivative of R ends up being this. Okay, product rule. And we want to know, well, when is this equal to 0? Well, this looks like a monstrosity. And I know that this is a calculator active question. So I'm going to go ahead and do one thing of algebra, and that's to factor out a t. I noticed that both terms have a t, so I'm going to factor that out. So I know that one critical point is that t is equal to 0. And for the other one, I'm going to use my graphing calculator to solve this. So let's get your graphing calculator going. I don't know what mode I'm in. I'm in radians. Okay. So here I am. I'm going to go ahead and I just want to graph what I have in parentheses there and figure out where that's equal to 0. So I'm going to enter in x cosine x, close that parenthesis, plus 2 sine t. So I have x cosine x plus 2 sine x, and I'm not sure what kind of window I need, but I know I can narrow this down. My time interval is between 0 and 3, so I'm going to put my t's between 0 and 3. All I care about really is I want to know where the derivative is 0, so I don't need a lot of y's. I'm just going to go from -1 to 1 because I only want to know where's the derivative equal to 0. So I graph this thing, and again, don't care what the shape is, just need to find my zeros. And right now I can see the first 0 is at 0, and I can see the second 0 on my screen is between 2 and 3. So I'm going to calculate the 0, and I need to go to the left, which would be, in this case, above my axis, and I need my right bound, and then my guess. And so this is what I get for my t is at 2.2889. So what I need to do is, if I'm ever going to use this value again, I need to store it somewhere. I'm not sure if I need it or not, so I'm going to go ahead and I'm going to store it in A. To do that, I'm going to quit. I'm going to hit X again, make sure that this is the X that I want, and I'm going to store it in alpha A. Again, I'm not sure if I need it yet. I'm going to do that anyway. So I'm going to write my answer down on my paper, and that I'm just going to give 4 decimal places. So these are my 2 critical points. Then the question is, when is the rate at which the water flows into the tank the greatest? Okay, so the greatest means I'm looking for a max. If I'm looking for a max, I'm going to have something like this, which means my function is going to change from increasing to decreasing, which means my derivative will change from positive to negative. So I'm literally going to go back to the graph on the calculator, and I'm going to look at that graph and see, does my derivative change from positive to negative anywhere? So looking at my graph, Does the derivative change from positive to negative? And it does. It changes from positive to negative right there. So I need to say that yes, it is greatest, the flow is greatest at 2.2889, but I also need to justify my answer. So to justify my answer, I need to explain what I've kind of written on the board in English, so to speak. So the rate that water flows into the tank is greatest at t is equal to 2.2889 because the derivative changes from positive to negative which means the function r changes from increasing to decreasing. And that indicates a max. So that is part A. Moving on to part B. Write an expression that represents the amount of water in the tank. Okay, so let me go back to the question. Sorry to scroll back up. We want to know how much water is in the tank. R is the amount of water going into the tank. Then we have this other thing, S, which is the amount of water flowing out of the tank. And again, those are rates. I want to know how much water is actually in there, which means what I need are some antiderivatives. So in part B, it's really just asking for an expression, and I can leave an antiderivative in an expression, so I'm going to. So I'm going to do the antiderivative of R minus the antiderivative of S, and I'm going to go from 0 to t on my bounds because that will give me any t value that I plug in, it will give me the amount of water. So that's going to be a of t is going to be the integral from 0 to 3 of r, which is t squared sine t, and I need to take out the definite integral from 0 to 3 of my s, which is 2 over t plus 1 squared dt. So that's it. That's just an expression for the amount of water in the tank. And stop here and look at these two things, and hopefully we'll recognize this. The first term there, t squared sine t, we cannot find the antiderivative of that. We can't. We don't know how. Now the second one we could actually find the antiderivative of, but the first one we can't, so we need to leave it alone just like it is. So part C is determine when there is the least amount of water in the tank. So the least amount of water, I'm looking for min of A. I want the minimum of A. So let's just start there. I'm going to ignore the rest of the question. Well, for now, we're going to answer it later. So I want the minimum of A. To find the minimum of A, I want to find the derivative of A and set it equal to 0. Well, I have A right there. A is an antiderivative. Fix your A. I am so sorry. Come back to your A and please fix this. We're not going from 0 to 3. That would only give me at time 3 how much water is in the tank. I apologize. So my expression should be from 0 to t. So sorry about that. So again, sorry. We're going to do a derivative now of that. So if I technically take the antiderivative of the first term, I plug in the t, I plug in the 0, I subtract, then I take the derivative of that, all I'm going to end up with is the same thing. So a prime of t is going to be t squared sine t minus 2 over t plus 1 squared. That's our derivative. That's it. Now, I want to know where that is equal to 0. And again, calculator active question, so let's go ahead and ask our calculator. So I'm going to go back to my calculator. I'm going to go to my y equals, and I'm going to put in this new expression for a prime. So I have x squared sine of x minus 2 divided by x plus 1 squared. I still have a dot on my calculator, sorry. And it won't go away. Okay. So I think that I've got the expression in my calculator. Let's check my window. Again, I'm going from 0 to 3, so that's perfect. I want to know where this thing's equal to 0, so my y-scale and x-scale are good. Let's take a look at this graph. So it looks like I have a critical point a little before 1, and that seems to be the only critical point that I have. So can we just look at the graph for a second and decide whether this critical point is going to be a maximum or a minimum? So my derivative goes from negative to positive at this critical point, which means my function goes from decreasing to increasing, which means at this particular critical number, I'm going to have a minimum, which is actually what I would like. So my minimum is going to be at this particular critical number. So let's calculate it. So we need to find the 0, and we've got a left bound. Sorry, I'm at 1.5. I need to go backwards. So I have a left bound, I have a right bound, I have guess, and I'm going to find my critical number here. Again, I'm a little paranoid. I'm going to go ahead and store this value. We already know that we have a minimum here, so I'm going to quit, get my x back on my screen, make sure it's right, and I'm going to store this, and let's put this in B, because I've already used A. So this has a critical number at t is equal to 0.86, oh, I've forgotten what it was, 8672. So now it says determine when there is the least. So I checked for the sign change of the derivative. This is a min is at t equals 0.8672 because the derivative changes from negative to positive. So a changes from decreasing to increasing. It says to, indicating a min. Okay, so that's sort of that part of that analysis leading to your conclusion. So next I need to know how much water is in the tank at this time. Well, I have an expression for the amount of water in the tank, and that's written in black at the top of the screen. That's my A. So all I need to do is plug in this t value up there. So all I'm going to do is I'm going to use my calculator to do this definite integral, and it's going to be A of 0.8672. It's going to be 0 to 0.8672 t squared sine t dt minus the integral from 0 to 0.8672 of 2 over t plus 1 squared. Now, I got to remember where I stored this. I stored this thing in B. So go back to your graphing calculator. Let's input this in fint. Mine's old school, so I apologize. You got new school. You do it new school way. So I'm going to have t squared. You know what? I have this in y1. I can just put y1 in here. Sorry, I typed in t squared sine t minus 2 over t plus 1 quantity squared. That's stored in my y1, so I don't have to type it in again. I go to vars, push the vars button, and I want a y vars, so I go over. I want a function, so I hit enter, and then I want y1, so I hit enter. So there's my y1. It's keyed in there, and now I just have to say with respect to x, and I need to go from 0 to B. Again, B. That's where I want to end. And when I work that out, I get a negative number. Sorry, you see my calculator is a little bit different. What I just realized is I missed part of the beginning problem because clearly we can't have a negative amount of water. So if we go back to the beginning, I'm going to scroll up. It told us something very important that I have neglected to even look at. And it says this right here. The tank initially holds 10 gallons of water. So before we even started with this water flowing in and water flowing out, there were 10 gallons of water in the tank. So I'm scrolling back down again. I need to fix my A of t. So my A of t is going to be how much flows in minus how much flows out, plus the initial 10 gallons that I had at the start of this water coming in and coming out. So my A should be this thing plus 10. So now when you look at my calculator, I took what I got from my definite integral and I added 10 to get the total amount of water in the tank as 9.201. So apologize for that. So now I need to write that down. So there will be 9.210. I don't remember if that's right. Hold on. 9.201 gallons. Okay, so there we go. We have our analysis in there. Good to move on. At this point, I know the video is 26 minutes long. I got one more problem to do, and it's not very long. So hang in there with me. I apologize. Okay, so for example 5. We have a differential equation. It's okay, chill out, everything is fine. Okay, so part A says, how do we know that 1 comma negative 2 is a critical point? Well, it's a critical point if dy dx is equal to 0. That means we have a critical point. So, plug in 1, negative 2 into our differential equation and see if we get 0. That's all we got to do. So, dy dx at the point 1 comma negative 2 is going to be equal to 2 times 1 plus negative 2, which is 2 minus 2, which is 0. So yes, because the derivative is equal to 0 at that point, we do have a critical point. So moving on to part B. Now, is this point going to be a relative max, a relative min, or neither? And we need to justify our answer. Now, with this derivative, because we have x's and y's in the derivative isn't very helpful past identifying that, yes, we have a critical point. So what we really want to do is we want to find the second derivative. So if I start with dy dx is 2x plus y. We start with this. I need to take the derivative of that to find the second derivative in terms of x, which means I need to deal with this y in a special way. So let's find this derivative. So the second derivative, the derivative of 2x with respect to x is 2 dx dx, and the derivative of y with respect to x is 1 dy dx. Again, that's really just our chain rule, our inside-outside rule. So now I need to know, well, using the second derivative, how is the second derivative going to help me? Well, if the second derivative is positive, second derivative positive, then the function is concave up, which means we have a min. And if my second derivative is negative, we are concave down, which means we have a max. So let's see what we have at this particular point. So now I need to figure out, well, what is the sign of my second derivative at 1 comma negative 2? And that's going to be 2 plus 1 times dy dx at 1 comma negative 2. I already found dy dx at 1 comma negative 2, and it's 0. Which means my second derivative is 2, which is a positive number, which means I have a positive second derivative. The function is concave up. So my second derivative is positive. So y is concave up. And that means that there is a min at that point, 1 comma negative 2. So there you have it. Sorry, just under 30 minutes. I apologize for the length of the video. I hope you have a wonderful evening. Bring all of your questions to class. Thank you.